Okay, so welcome back, and we were in the discussion of ARM programming. So we discussed about the typical program flow, the workflow that we are supposed to do in developing the programs. We also briefly discussed about the architecture of an ARM program, the certain ways that you write the code, and I ask you to please strictly follow that because that's very important. Let it become a habit so that you get used to it, and it helps a lot. And now we are slowly going into the real heart of it, right? The instruction set itself. Okay, so if you remember, our 8-bit microcomputer had very limited data set, instruction set rather. So it had the LDA command, which you are very comfortable by now. Then it had the add and sub command, then it had the halt command, and then it had the out command. So it was very limited instruction set. But on the other hand, any modern day microprocessor or microcontroller that you take, you will essentially have a lot more options, and we already saw that the ARM Cortex M4 series had a sea of commands, right? An ocean of instructions, you could say. But M0 Plus or M0, it's just restricted to 56 of them. And the categories, if you really broadly classify them, it's something like the data processing instructions. So basically will include the arithmetic, add, sub, those related instructions. Then the logical instructions, the shift instructions, logical and the shift instructions. Then you have the data movement, load, store, and the move instructions. So that's the bunch. And then of course for the programming per se, you do have the branch and control instructions, like it's like the if loop, while loop, for loop, etc., that you generally write in the C code, right? So they get transferred or transformed to a branch or a control instruction. So that's the thing. And then we do have some miscellaneous instructions, something like breakpoint and all those things, which we may not use that much, but it's worth to notice them as well. Okay, so in a nutshell, if you go back, I took it from the textbook. So if you just see there, you can actually consider again. We know that our ARM Cortex M0 Plus supports thumb 1 and thumb 2. So these are the thumb 1 instructions, the 16-bit instructions. So most of them we will study in detail. Some of them I'm leaving it to you for your self-learning. So you can always go back and refer the manual, which will be given to you in as part of the lab instructions. So please download them and keep it aside with you so that you can always refer that. Okay, don't by heart anything because that's not needed. You just need to understand what is the instruction is doing, which could come from the reference manual itself, and make use of this to write all your programs. So these are the 16-bit and then the 32-bit instructions. So the branch with label is here. Then you have the move operation to special registers. So we will discuss about them later on. And then some special commands, which I don't see them being used, but it's worth to have a look at it and understand as well. Okay, so even here also sorry, we may not be using all the commands. So yeah, interesting to note there's BL here, and at the same time there's a branch B and BLX, BX. All these are branch statements, but they are 16-bit compared to this. This is like there is no operand given, it's just the mnemonic alone that occupies 32-bit compared to this specific purpose for it. So we'll learn that as we go along. Okay, so let's now dig a deep dive into some of the instructions. So it is boring if I just keep on explaining about the instructions. You can learn it by yourself. My objective is to give a brief overview, and I will also help you with some particular examples using Keel, which you also should try out because at the comfort of your laptop. Okay, so let's move on. So this is we will start with the load and store instructions. So a bunch of them are available, and many of them may not be available to you in the simulation mode. And for the board also, the freedom board also, not every one of them will be supported. So the NXP semiconductors, when they map the ARM licensed Cortex M0 Plus to their fabrication system, they may not actually give provision to have all the commands. So some of them will fail. But generally, if you are working on Cortex M0 Plus, all these commands are supposed to be supported. Okay, so a brief explanation. Let me actually start with the easier one. So LDR, register number here. So you have R0 to R12, right, for you to play with, and then you can give some address Okay, so this can be a label which has the data which has to be loaded to. So this is like a pointer or the address which can be loaded to this register RT. So you have the mnemonic, then you have the target, and then you have the source. So that's the format we always follow. And there is something very interesting format. You can actually load the full 32-bit data. It's something like this. So let's say you have the address in a register. Okay, so you already loaded. So you can use this command to load the address location, and then you can use this command to load the data. So you might have seen this particular usage here. So let me actually use the pen. Okay, so I'll have examples, so don't worry. So I'll just put some example here. So let's say LDR R0 some label name. Let's say just give some name. So let's say data. Okay, so this is a label. That means it's a pointer to some data which I have it in memory, and I'm going to actually load R0 with that address location, that data address locations. That's the meaning of this. So this is corresponding to this guy. Okay, so this statement. Then what I can do is something like LDR R1. Okay, and then how something like this. So this bracket has a meaning. So it means that I'm not interested in loading content of R0 into R1, but rather I'm interested in loading the content of R0. Okay, so something like R0, for example, here has the address of this particular location, right, memory location. So when I have this bracket, it means that whatever is the content of that address location will be loaded to R1. So let me put some example to prove that point. So this is some memory. Okay, so let's say it has some memory location. I'm just putting some number. Okay, so we have 32 bits, so I have to have this many. So it's a hexadecimal, so you have 8 of them, right? Each one is 4 bits. So you are going to, let's say this is in your code, this is your data. Okay, so this is the location. So this means after the execution of this line, R0 will be having this particular address, and then R1, what will be having after this is actually whatever is the content here. This content will be loaded in R1. Okay, so that's the meaning of it. So this is R0. So R1 will have this XX, whatever is the content, which is actually stored in here, and this is actually what is shown here. Okay, so there is an option to give an offset also. So you can actually, instead of having R0, what you can actually do is some increment to the address. So let me actually remove this. So basically what you can do is, let's say I'm going to put some hash 4. Okay, so this means that we will have R0 is pointing to this location, but you are adding 4 address location, so it will just skip. So it will skip this one, this one, this one, and this one, and this will be the new address. So R0 plus 4, whatever is the content here, will come to R1. So that is the meaning of this particular statement. Okay, so similarly there is an option. So here the entire 32-bit will be stored if I use this command, but if I want just the byte, just the 8 bits, okay, I don't want the full data but only the 8 bits, then you can use this command. I will have example for this. So then the 16 bits, this is the command, and there is sign bit also. So basically for example sign byte I'm saying, so only 8 bits are stored, but the remaining basically 24 bits, right, because it's a 32-bit data that we are talking about, but 8 bits it's only going to be replaced. The remaining 24 bits, most significant 24 bits of RT, they can be made as sign extension of the most significant bit in the 8-bit data which is loaded. So there is a possibility like that. So I will explain that in the next slide. And then we do have the option to load into multiple registers. Okay, so you can actually give multiple registers here, R0 to R7, and then you can store from a bunch of, so if we have a label here, the entire registers, the full register bank will be filled. So instead of one register at a time, I can fill multiple registers at a time. So that is what this load multiple registers means. Similarly, you can store multiple register. You can store from basically this whatever is content in this register can be actually stored into the address specified by this location. Also, you can store by bytes. You can store by half word also. So that's the entire load and store instruction. Let me give an example. Okay. So this is an interesting example. So I have priorly filled the data, the memory location 0, 2, 0, 0, 0, all zeros with this one, then first with this one, and then 2 with this one. So this is a memory. This is somewhere in the memory. These are the address values and these are the data values. So remember, it's all 8-bit data. Okay, so the content, the address may be having 32 bits, but the data is always 8 bits. We have mentioned that in before lectures also. So this is F2, this is E1, 34. So 12 is the content in this particular address location. That is the meaning of it. Now let's put some commands. So let's say assume I have already loaded R0 with this particular address location. So basically I can do it straight forward. So LDR R0, then this particular address location I already have in R0. Okay, so R0 is like a pointer to this particular address location. So that's the meaning of it. Now if I use this command LDR R1 content of R0, what is going to happen is R0 is this, so content of this particular guy is this particular thing, and here I am going to load the full 32 bits, right? So this is only this is the guy, this is only 8 bits, but then since I am asking for 32 bit, it will go to 1, 2, 3 afterwards, right? So that is the case. So that's why all this R1, this is the content of R1 I am showing over here. So let me actually make it clear so that you don't have any confusion. But anyway, you will play with this, right? So R1 is this particular entire 32 bits. Okay, so this is 8 bit, 8 bit, 8 bit, 8 bit. So what is going to happen is this, even though R0 has only the location of this, so this will be loaded to the lowest byte, and then this one, because we are asking for all 32 bits, so this is another 8, so 16 bits, then this is 24 bits, and then this is 32 bits. So the entire chunk will come to R1. So that is the meaning of it. So I will show this to you. Okay, and then of course if I do this particular thing, that means actually only the half word is stored, that means 16 bits. So if I give same command, then only these two will come and this 2 will come into R1. The remaining is actually 0. If it was initially 0, this register R1 was initially 0, then this will remain 0, only the 16 bits will come into the picture. And then of course if you do this, that means byte only, so that means only this guy will be accessed, and that is what actually coming here. Then there is this option of sign extension I was talking. So if I do this, so this is like LDR SH, that means signed extended half word. So you take these two data and then you put it in these two places, but then what is the sign bit of this particular data? That means the most significant bit, which is actually E is nothing but, so let me put the E, if I expand E is nothing but, so I'll put it here, so E is nothing but 1110, right? So the most significant bit is having 1, so that will be extended, so that is extended throughout here, so that's 11111111 all 1, so that is FFF. So if most significant, so suppose the data here was something like 11 0x11 here, so that means it is 0001, right? So then this 0 will be extended in these locations. So that is the meaning of it. So you extend the sign bit. Okay, so that's the literal thing, but very rarely we use all these, but it may be used in some of the codes. I can't immediately think of an application, but yeah, there may be some application to it. Okay, you may be thinking, where is it used, right? Yeah. Okay, so then this half word, you can do it for the byte also. Again here F means 1111, that is why all of them became 1, all ones, because the sign bit is extended. So that's the thing. So let me actually quickly show this part in Keel so that you get a feel of what I'm talking about, and then we will convey the rest of the things. Okay, so let me actually do that. Okay, so this is the code I have written in Keel, again following the format that we have mentioned in the previous lecture. So you have the code section, which sort of covers till here, and then you have a data section which sort of does it here. So this is interesting. So the same example, I'm going to use the same example. So this particular example, I'm going to store these data. So in fact I don't have control on the address location. I can do that, but I am not giving any strict control. So this is what I am going to store in the data. So F2, E1, 34 and 12. So that's what actually here. So you can actually see it here. So some location label is array, so that is actually stored with these particular 4 values. And then what I'm doing in the code is very interesting. So I'm going to load R0 with this pointer, this address. So whatever is this address location, which is when the system gets compiling, I mean when the the compiler compiles this code, the array becomes an address location. That address location will be stored in R0. And then what I'm going to do is LDR R1 this basically. So whatever is these 4 contents which are there in this location will get stored in R1. And then I'm going to use RH, that means only half word from this, that means only these 2 things will be stored. And then of course LDRB, which means only this will be stored. And you will be able to see that R1 values getting changed real time. Okay, so we are going to do in simulation mode, but when you are having the board with you, you can always go and test it in the actual hardware. Okay, so that's important aspect. So I commented these 2 code because it will not work in the board. In the simulation mode we have to try whether it works in the actual but I don't think so. It's not really that way. So these codes are restricted. It's not really working on our freedom board. Okay, so it doesn't work, these 2, but I just put it for the full reference. So now let's actually build this. So let me just see there are any errors for this. There's no errors, there's no problem. And now let me go to the debug option. So I'm going to start the debug, and all these codes I'm just going to reiterate for you. So it started with the reset handler, and then of course some export import things are there. And now first step is to disable all the interrupts, user defined interrupts. So I disabled it. Now I will load the address of my system initialization file. So that's what happening here. Again same command. Now you will be able to understand what is happening here. So R0 will be loaded with the address location of my system initialization instructions. Okay, so that's loaded. Now what is going to happen is, you didn't study the branch, but this is something like branch to this address. So basically it means that go and execute whatever is written in this particular address. So that's going to happen. So moment I execute this will go to system initialization. Yeah, we are already in the system initialization. And this is written in C. So you can see that you can mix and match the assembly and the C. That's a beauty. Okay, so let's do some. So we will come back to this part again. So this is like initializing some clock and all these things, which will come back later. We are back. So the clock is started up and running. So you are back in the code. Now you are going to enable the interrupts, and then basically what you're going to do is load the address of the main function. So again you go back and see we have put a location main. That's why I suggested you to not change this. If you want to change this value name, you should go back and you should go to this particular location and change this value, because at the reset handler, after executing the system initialization, it is going to execute the main whatever is written. So you change your name here, and then you are free to change the name here. But if you are sticking to this name, default name, you should always put that name here. So let's do that. So the address is loaded again to R0, and then you are branching to that particular location. So that is exactly this. You are already in here now. So R0 at this point we will have some random location, which was actually the address location of this particular thing, but let's ignore that, because once you write this, it is going to load the address of this particular data. So let's do that. Yeah, it is loaded. Okay, so let me actually show you that. So if you go and see this bottom, there is a memory option. So you can actually put these values 0xxx. So let me see 1 2 4. Okay, so you can see the data. This is actual memory location. You can see that 124 has F2, 125 has E1, 126 has 34, and 127 has 12. So that's literal meaning. So 24 location. So 124, 125, 126, 127. That's what we are storing, right? So that's the address location. Now here what I'm going to do is R0, that is having this particular address, and that content 32 bits, that means all the 4 groups locations together will be loaded to R1. R1 is at this point 0. The moment I execute this line, you will see this F2, E1, 14, 12 in the other order, right? Because this is a more significant byte, because that's storing at the most significant location. So that will come. So let's see that. Yeah, so you can see 12, 34, E1, F2. So that is actually there in R1. Now in this case, next command, I'm only going to do half words. So that means only E1 and F2 will store. The remaining, I'm not doing sign extension, so remaining will be all 0. So just notice R1. Have a look at R1 here, and you will see the change. Yeah, You can see it 0 0 0 0, those are not changed, but even F2, which is actually these two locations, that will be stored. Similarly, the last line is byte, so you can see it over here, all of them will be 0 except the last two locations, which are the 1 byte of data, which is nothing but F2. So that's it, and now it will remain here because it is B here, right, and here is here itself, so it will be like an infinite loop. It will be stuck like the halt operation that we do. Okay, so that's it. So I hope it's pretty clear to you. Let me actually minimize this and then come back to the slides and then continue. So this, I hope it's pretty clear to you. So the other options, so you can actually I already told, instead of R0 I can add a location, the buffer of 4. This means that the address location, the pointing to the address location, which is R0 plus 4, not R0. So this is, for example, let's say some this is some address locations and some data stored, and let's say R0 is stored with this data which is pointing to here. Okay, so that's pointing to here. So if I put offset 4, which is actually R0 plus 4, it will be pointing to this location. And then if I do this one, R1, the same command, this particular command, literally what is going to do is, so these 4 data starting from this R0 plus offset 4, so that means 5B, 6A, 79, 88. So R1 will be having those. So 88 is of course the most significant byte, so it comes there, and then 79, then 6A, 5B. So if I had put no 4 here, it would have been 4C, 3D, 2E, 1F. But since I incremented by a 4, an offset of 4, this is the way to go about. So these are the possibilities. So this is not available for Cortex M0 Plus, but there is an option to, if I do this particular thing, so what is going to happen is memory of R0 plus R4 will be stored in R1, and then R0 will be automatically incremented by 4. So R0 will not stay at whatever address location we initially loaded, but it will also get incremented. So that is the important thing. Some other options, it's self-explanatory, not very difficult. Okay, so and the offset can range from minus 255 to plus 255. So the reason is, actually, if you see here, you have something like this entire this one is 32 bits, so LDR will occupy something like this yeah, you can see something like, let's say, I'm just saying the R1 basically the what it essentially says is this particular offset can take 8 bits, right? That's why it can go from not 8 bits, actually 2 raised to 7 is 128, 2 raised to 8, 2 raised to 9, right? So 9 bits you can take. That's why it's minus 255 to plus 255. That's offset you can give. Okay, so let's move on. So this is this, and then yeah, store operations, some example. I suggest you to actually try all these in the Keel. I'm not going to show you a lot of examples, but you can actually try this out and see how this is working. So here again the literal meaning is, so the data again is here with some address location, and let's say R1 is having this particular location or this particular data, and R0 is having this particular location. So what is going to happen is, after this execution, so you can see over here, so R0 plus 4, right? R0 is pointing to this location. So let me actually put it. So R0 is pointing to this location, but this command is pointing to this particular location, right? Because it's offsetted by 4, and then R1 content will be stored to this particular location. So this is R1 content, it is stored in these 4 locations. So that's the literal meaning. And again, 88 should go to the most significant or the highest address, and 5B is going to the lowest address. So that's the way. So this is store command, just the opposite of the load command. Okay, and then the multiple option, so you can load multiple registers or get updated multiple registers or store multiple registers onto the memory. So this is an option. So let's say R0, R1, R2, R3 has these 4 locations. Okay, so that's the literal meaning of it. And then if I do this, so R0, this R1 to R3, so R0 is the address location. Okay, this is the memory address location. So what I'm going to literally do is, I'm going to actually put into this location the contents in R1 to R3. So all these 3 contents will be actually put into this particular address location. So after this, there is no change to R1, R2, R3 and R0, but in the memory location, you might see, if you see in the keel this memory location, it might have updated with these 3 register values. Okay, so that's the literal meaning of it. And then of course this is another way to get back that data. So please try this out. So you have LDR R0, so you're going to load this location again. Okay, and then you want to move. So move command you didn't study yet, but this is a good way to actually see what is it doing. So you are basically corrupting R1, R2, R3 with some 1, 2, 3 some data. Okay, so after this execution, your R1, R2, R3 is corrupted. Now I can store the data or return the data back by actually you can see after this, these are the values stored in R1, R2, R3. And if I do this command actually, so R0 is having this particular location. This actually means I'm going to load to R1 to R3 the content from R0. So this is going to happen. So you see R0 is incremented. So I think I didn't mention. If I have this exclamation mark here, it means that R0 value will get incremented based on this particular thing. So that's what essentially happens. So you have these values back. So this is something which is pretty easy to illustrate, or pretty interesting to illustrate the LDM STM option. So you can store multiple register values onto the memory, as well as you can load multiple data from memory to register bank instead of operating at a single register level. Okay, so that's the beauty about this. So let me actually quickly show you again this part in the keel before I move on. Okay, so welcome back. So this is the code I've just written, which sort of mimics this part, and there is a small mistake here which I realized after reading. There is 1 byte extra because you have 1, 2, 3, 4, 5, 6. Just a minute. I think this is basically the reason I made a small mistake here. It's very simple. If I do the let me just first see this and then get back to you. So you can see over here, if I go to the memory map debug, you can go to memory map to see where all we can write and read. So of course these are read write, so this is one option. The other option is like from 1FFF0000. so I think in that sense I made a mistake here. It is 1FFF0000, right? So that's the thing, I made a small mistake. Let me just go back to the code and explain to you. So this is basically some location I'm giving. I'm trying to give this location, so I'll just do everything here. Okay, so yes, so this is the address location that we will be playing with, because I found that the other one is not correct. So please let me correct this and make it uniform for all the. So basically 1F was missing, so I corrected everything, but you can always check it. So it doesn't matter this code, but this slide, because you can always give a try here. So let me just go back to this. Yeah, so this is a code. So what we are going to do is, this is some address location which is sort of read writable for us. So that is what stored in R0, and then R1, R2, R3 I am storing the values as in the slide. And then using this multiple store option, what I am going to do here is, this guy R0, this address location is loaded with the contents in R1 to R3, and then of course the content in R0 is also incremented. That is what this exclamation means. So how many registers are here? So it's like R1, R2, R3, so 3 registers. So the address location will also get incremented by how much? So that's a trivia for you. Just pause and think about it. What is the value? So just imagine that each register is a 32-bit register. So you are having 3 such registers. You have to increment it by not just it's like the address location. Always remember, each location stores only 8 bits. So you will see that the value will get incremented. The R0 value will get incremented to C. Okay. So basically it's something like you increment for 1 register, it's like 4 locations. You increment for 2 registers, it's like 8 locations. You increment for 3 registers, it's like 12 locations, and 12 is nothing but C, right? ABC. Okay, so that's the thing. Okay, so let's do this, and then of course once you store this, the R0 will become something like C here. instead of 0, and then I'm corrupting R1, R2, R3 by moving 1, 2, 3. There is one more mistake I made, sorry. So the move command is not supported, only move S will be supported. What is the difference of move and move S, we will discuss in the next few slides. So let me make that correction also. I think I didn't do that. Okay, so let me make that as well. I am doing it together because I realized I made this mistake, and instead of correcting on the fly, I thought explain to you and correct it just like in a classroom. Okay, so that's it, we corrupted it, and then what we are going to do is we are going to load again this R1, R2, R3 with whatever is the content in R0, and again I'm incrementing the address of R0 after the loading. So what is going to happen is these three contents will come back in R1, R2, R3. So that's the scenario. So let's actually do this. So I am going to build it. So you can use this button also instead of going to project and build. It is same. So you can scroll and see it's built, and then I am going to run it. Okay, so now let's go through this till the time it goes to main. Yeah, so R0 will be first of all loaded with that address, which is done. Then R1, R2, R3 is loaded with these values, so it is also done. Now you are having this particular address, so you can see the address is changed to C. That is because you stored 12 locations, you incremented 12 locations, right? So that's the reason why R0 is incremented by C. C is equivalent to 12 in decimal. So hexadecimal C is equivalent to 12 in decimal. That's what I mean. Okay, so now I'm going to reload R0 with the original address. So that's what done. Okay, so yeah, in fact you can see over here also, if you search that address, this is updated. Okay, so this is updated with 9, 8 and 7. So you can see that. And now if I do corrupt the R1, R2, R3 with 1, 2, 3, which I did it using this move command, and now I'm going to load that register value, whatever is this particular address, back to R1 to R3. So let's actually do that. Yeah, it's done. So 7, 8, 9. Okay, so R3 is loaded with 7, 8, 9 as before. So we recovered the data fully. Okay, so it's pretty interesting. I hope you understood it clearly here. Okay, so I hope this part is pretty clear, and there is no issue here. So we will stop this lecture for the moment, because you can always play with this example, and hopefully you understood the load and store operation pretty clearly. I think we will stop the video for this week. Let's not hurry up. So we'll go into the other instructions in the next week, which is mostly the move instructions, then the arithmetic logical instructions, then the branch instructions. So those are more interesting instructions coming up, and instead of I'm hurrying up and adding a lot of input to you, let's actually do it next week. Okay, so till then it's bye from my side. Thank you.